In mathematics, a self-adjoint operator on a complex vector space V within a product is an operator that is its own adjoint. If V is finite-dimensional with a given orthonormal basis, this is equivalent to the condition that the matrix of A is Hermitian, that is, equal to its conjugate transpose A. By the finite-dimensional spectral theorem, V has an orthonormal basis such that the matrix of A relative to this basis is a diagonal matrix with entries in the real numbers. In this article, we consider generalizations of this concept to operators on Hilbert spaces of arbitrary dimension. Self-adjoint operators are used in functional analysis and quantum mechanics. In quantum mechanics their importance lies in the Dirac-von Neumann formulation of quantum mechanics, in which physical observables such as position, momentum, angular momentum and spin are represented by self-adjoint operators on a Hilbert space. Of particular significance is the Hamiltonian, which as an observable corresponds to the total energy of a particle of mass m in a real potential field V. Differential operators are an important class of unbounded operators. The structure of self-adjoint operators on infinite-dimensional Hilbert spaces essentially resembles the finite-dimensional case. That is to say, operators are self-adjoint if and only if they are unitarily equivalent to real-valued multiplication operators. With suitable modifications, this result can be extended to possibly unbounded operators on infinite-dimensional spaces. Since an everywhere-defined self-adjoint operator is necessarily bounded, one needs be more attentive to the domain issue in the unbounded case. This is explained below in more detail. Symmetric operators. A linear operator A on a Hilbert space H is called symmetric if, for all elements x and y in the domain of A sometimes, such an operator is only called symmetric if it is also densely defined. More generally, a partially defined linear operator A from a topological vector space E into its continuous dual space A, is said to be symmetric if, for all elements x and y in the domain of A. This usage is fairly standard in the functional analysis literature. A symmetric everywhere-defined operator is self-adjoint. By the Hellinger-Toeplitz theorem, a symmetric everywhere-defined operator is also bounded. In the physics literature, the term Hermitian is used in place of the term symmetric. It should be noted, however, that the physics literature generally glosses over the distinction between operators that are merely symmetric and operators that are actually self-adjoint. The previous definition agrees with the one for matrices given in the introduction to this article. If we take as H the Hilbert space Cn with the standard dot product and interpret this square matrix as a linear operator on this Hilbert space. It is however much more general as there are important infinite-dimensional Hilbert spaces. The spectrum of any bounded symmetric operator is real. In particular all its eigenvalues are real, although a symmetric operator may have no eigenvalues. A general version of the spectral theorem which also applies to bounded symmetric operators is stated below. If the set of eigenvalues for a symmetric operator is non-empty, and the eigenvalues are non-degenerate, then it follows from the definition that eigenvectors corresponding to distinct eigenvalues are orthogonal. Contrary to what is sometimes claimed in introductory physics textbooks, it is possible for symmetric operators to have no eigenvalues at all. The example below illustrates a special case when an symmetric operator does have a set of eigenvectors which constitute a Hilbert space basis. The operator A below can be seen to have a compact inverse, meaning that the corresponding differential equation F equals G is solved by some integral, therefore compact, operator G. The compact symmetric operator G then has a countable family of eigenvectors which are complete in L2. The same can then be said for A. Example. Consider the complex Hilbert space L2, 0, 1, and the differential operator. Defined on the subspace consisting of all complex-valued infinitely differentiable functions f on, 0, 1, with the boundary conditions f, 0, equals f, 1, equals 0. Then integration by parts shows that A is symmetric. Its eigenfunctions are the sinusoids, with the real eigenvalues n2 I2 The well-known orthogonality of the sine functions follows as a consequence of the property of being symmetric. We consider generalizations of this operator below. Self-adjoint operators. A densely defined linear operator on a Hilbert space is self-adjoint if it equals its adjoint. Given a densely defined linear operator A on H, its adjoint A is defined as follows: the domain of A consists of vectors X in H such that, which is a densely defined linear map, is a continuous linear functional. By continuity and density of the domain of A, it extends to a unique continuous linear functional on all of H. By the Rice representation theorem for linear functionals, if X is in the domain of A, there is a unique vector Z in H such that this vector Z is defined to be AX. It can be shown that the dependence of Z on X is linear. Notice that it is the denseness of the domain of the operator, along with the uniqueness part of Rice representation, that ensures the adjoint operator is well defined. A result of Hellinger-Toeplitz type says that an operator having an everywhere defined bounded adjoint is bounded. The condition for a linear operator on a Hilbert space to be self-adjoint is stronger than to be symmetric. Although this distinction is technical, it is very important. The spectral theorem applies only to operators that are self-adjoint and not to operators that are merely symmetric. For an extensive discussion of the distinction, see Chapter 9 of Hall. For any densely defined operator A on Hilbert space, one can define its adjoint operator A. For a symmetric operator A, the domain of the operator A contains the domain of the operator A, and the restriction of the operator A on the domain of A coincides with the operator A, that is, A', in other words A is extension of A. For a self-adjoint operator A, the domain of A is the same as the domain of A, and A equals A. See also extensions of symmetric operators and unbounded operator. Geometric interpretation equals. There is a useful geometric way of looking at the adjoint of an operator A on H as follows. We consider the graph G, A, of A defined by theorem. Let J be the symplectic mapping. Then the graph of A is the orthogonal complement of JG, A. A densely defined operator A is symmetric if and only if A', where the subset notation A' is understood to mean G, A, G, A. An operator A is self-adjoint if and only if A equals A. That is, if and only if G, A, equals G, A. Example. Consider the complex Hilbert space L2, R, and the operator which multiplies a given function by X. The domain of A is the space of all L2 functions for which the right-hand side is square integrable. A is a symmetric operator without any eigenvalues and eigenfunctions. In fact, it turns out that the operator is self-adjoint, as follows from the theory outlined below. As we will see later, self-adjoint operators have very important spectral properties. They are in fact multiplication operators on general measure spaces. Spectral theorem. Partially defined operators A, B on Hilbert spaces H, K are unitarily equivalent if and only if there is a unitary transformation U, H or K such that U maps DOM A bijectively onto DOM B. A multiplication operator is defined as follows: let B a countably additive measure space and F a real-valued measurable function on X. An operator T of the form whose domain is the space of I for which the right-hand side above as in L2 is called a multiplication operator. Theorem. Any multiplication operator is a self-adjoint operator. Any self-adjoint operator is unitarily equivalent to a multiplication operator. This version of the spectral theorem for self-adjoint operators can be proved by reduction to the spectral theorem for unitary operators. This reduction uses the Cayley transform for self-adjoint operators, which is defined in the next section. We might note that if T is multiplication by F, then the spectrum of T is just the essential range of F. Borel functional calculus equals, given the representation of T as a multiplication operator, it is easy to characterize the Borel functional calculus. If H is a bounded real-valued Borel function on R, then H, T, is the operator of multiplication by the composition HAF. In order for this to be well defined, we must show that it is the unique operation on bounded real-valued Borel functions satisfying a number of conditions. Resolution of the identity equals, it has been customary to introduce the following notation. Where is the characteristic function of the interval? The family of projection operators et, I is called resolution of the identity for T. Moreover, the following Schild's integral representation for T can be proved. The definition of the operator integral above can be reduced to that of a scalar-valued Schild's integral using the weak operator topology. In more modern treatments, however, this representation is usually avoided, since most technical problems can be dealt with by the functional calculus. Formulation in the physics literature in physics, particularly in quantum mechanics, the spectral theorem is expressed in a way which combines the spectral theorem as stated above and the Borel functional calculus using Dirac notation as follows: if H is self-adjoint and f is a Borel function, with where the integral runs over the whole spectrum of H. The notation suggests that H is diagonalized by the eigenvectors i.e. such a notation is purely formal. One can see the similarity between Dirac's notation and the previous section. The resolution of the identity formally resembles the rank 1 projections. In the Dirac notation, measurements are described via eigenvalues and eigenstates, both purely formal objects. As one would expect, this does not survive passage to the resolution of the identity. In the latter formulation, measurements are described using the spectral measure of, if the system is prepared in prior to the measurement. Alternatively, if one would like to preserve the notion of eigenstates and make it rigorous, rather than merely formal, one can replace the state space by a suitable rigged Hilbert space. If f equals 1, the theorem is referred to as resolution of unity. In the cases the sum of an Hermitian H and a skew Hermitian operator, one defines the bi-orthogonal basis set and write the spectral theorem as see Fano partitioning method for the context where such operators appear in scattering theory. Extensions of symmetric operators. The following question arises in several contexts: if an operator A on the Hilbert space H is symmetric, when does it have self-adjoint extensions? An operator that is a unique self-adjoint extension is said to be essentially self-adjoint, but a symmetric operator may have many or no self-adjoint extensions. Thus, we would like a classification of its self-adjoint extensions. One answer is provided by the Cayley transform of a self-adjoint operator and the deficiency indices. Theorem. Suppose A is a symmetric operator. Then there is a unique partially defined linear operator, such that here, Ran and Dom denote the image and the domain, respectively. W, A, is isometric on its domain. Moreover, the range of 1 W, A, is dense in H. Conversely, given any partially defined operator U which is isometric on its domain and such that 1 U is dense, there is an operator S, U, such that the operator S, U, is densely defined and symmetric. The mappings W and S are inverses of each other. The mapping W is called the Cayley transform. It associates a partially defined isometry to any symmetric densely defined operator. Note that the mappings W and S are monotone. This means that if B is a symmetric operator that extends the densely defined symmetric operator A, then W, B, extends W, A, and similarly for S. Theorem. A necessary and sufficient condition for A to be self-adjoint is that its Cayley transform W, A, be unitary. This immediately gives us a necessary and sufficient condition for A to have a self-adjoint extension, as follows. Theorem. A necessary and sufficient condition for A to have a self-adjoint extension is that W, A, have a unitary extension. A partially defined isometric operator V on a Hilbert space H has a unique isometric extension to the norm closure of DOM, V. A partially defined isometric operator with closed domain is called a partial isometry. Given a partial isometry V, the deficiency indices of V are defined as the dimension of the orthogonal complements of the domain and range. Theorem. A partial isometry V has a unitary extension if and only if the deficiency indices are identical. Moreover, V has a unique unitary extension if and only if the deficiency indices are both zero. we see that there is a bijection between symmetric extensions of an operator and isometric extensions of its Cayley transform. The symmetric extension is self-adjoint if and only if the corresponding isometric extension is unitary. A symmetric operator has a unique self-adjoint extension if and only if both its deficiency indices are zero. Such an operator is said to be essentially self-adjoint. Symmetric operators which are not essentially self-adjoint may still have a canonical self-adjoint extension. Such is the case for non-negative symmetric operators. These operators always have a canonically defined Friedrichs extension, and for these operators we can define a canonical functional calculus. Many operators that occur in analysis are bounded below, so the issue of essential adjointness for these operators is less critical. Self-adjoint extensions in quantum mechanics equals, in quantum mechanics, observables correspond to self-adjoint operators. By Stone's theorem on one-parameter unitary groups, self-adjoint operators are precisely the infinitesimal generators of unitary groups of time evolution operators. However, many physical problems are formulated as a time evolution equation involving differential operators for which the Hamiltonian is only symmetric. In such cases either the Hamiltonian is essentially self-adjoint, in which case the physical problem has unique solutions, or one attempts to find self-adjoint extensions of the Hamiltonian corresponding to different types of boundary conditions or conditions at infinity. Example: the one-dimensional Schrödinger operator with the potential, defined initially on smooth compactly supported functions, is essentially self-adjoint for 0-2. See Beeresin and Schieben, pages 55 and 86, or section 9.10 in Hall. Example: there is no self-adjoint momentum operator P for a particle moving on a half-line. Nevertheless, the Hamiltonian of a free particle on a half-line has several self-adjoint extensions corresponding to different types of boundary conditions. Physically, these boundary conditions are related to reflections of the particle at the origin. Von Neumann's formulas: suppose A is symmetric densely defined. Then any symmetric extension of A is a restriction of A. Indeed, A'(B) and B symmetric yields B'(A) by applying the definition of Dom. A. Theorem. Suppose A is a densely defined symmetric operator. Let then and where the decomposition is orthogonal relative to the graph inner product of Dom. A. These are referred to as von Neumann's formulas in the Akiza and Glasman reference. Examples: we first consider the differential operator. Defined on the space of complex-valued Carl functions on 0, 1, vanishing near 0 and 1. D is a symmetric operator as can be shown by integration by parts. The spaces n+, now are given respectively by the distributional solutions to the equation, which are in L2, 0, 1. One can show that each one of these solution spaces is one-dimensional, generated by the functions xax and xax respectively. This shows that D is not essentially self-adjoint, but does have self-adjoint extensions. These self-adjoint extensions are parametrized by the space of unitary mappings n plus n r, which in this case happens to be the unit circle T. This simple example illustrates a general fact about self-adjoint extensions of symmetric differential operators P on an open set M. They are determined by the unitary maps between the eigenvalue spaces, where P(dist) is the distributional extension of P. We next give the example of differential operators with constant coefficients. Let be a polynomial on Rn with real coefficients, where I plus or minus ranges over a set of multi-indices. Thus, and we also use the notation. Then the operator P, D, defined on the space of infinitely differentiable functions of compact support on Rn by, is essentially self-adjoint on L2, Rn. Theorem. Let P a polynomial function on Rn with real coefficients, f the Fourier transform considered as a unitary map L2, Rn, L2, Rn. Then Fp, D, f is essentially self-adjoint and its unique self-adjoint extension is the operator of multiplication by the function P. More generally, consider linear differential operators acting on infinitely differentiable complex-valued functions of compact support. If M is an open subset of Rn, where I plus or minus are infinitely differentiable functions, P is a linear operator. Corresponding to P there is another differential operator, the formal adjoint of P. Theorem. The adjoint P of P is a restriction of the distributional extension of the formal adjoint to an appropriate subspace of. Specifically, spectral multiplicity theory, the multiplication representation of a self-adjoint operator, though extremely useful, is not a canonical representation. This suggests that it is not easy to extract from this representation a criterion to determine when self-adjoint operators A and B are unitarily equivalent. The finest-grained representation which we now discuss involves spectral multiplicity. This circle of results is called the Hahn-Hellinger theory of spectral multiplicity. We first define uniform multiplicity. Definition. A self-adjoint operator A has uniform multiplicity n where n is such that 1 a per mole currency n a per mole currency I per mole if and only if A is unitarily equivalent to the operator mf of multiplication by the function f, I equals ion. Where Hn is a Hilbert space of dimension n. The domain of MF consists of vector-valued functions ion are such that non-negative countably additive measures I1/4, I1/2 are mutually singular if and only if they are supported on disjoint Borel sets. Theorem. Let A be a self-adjoint operator on a separable Hilbert space H. Then there is an I per mole sequence of countably additive finite measures on R, such that the measures are pairwise singular and A is unitarily equivalent to the operator of multiplication by the function f, I equals ion. This representation is unique in the following sense: for any two such representations of the same A, the corresponding measures are equivalent in the sense that they have the same sets of measure 0. The spectral multiplicity theorem can be reformulated using the language of direct integrals of Hilbert spaces. Theorem. Any self-adjoint operator on a separable Hilbert space is unitarily equivalent to multiplication by the function IA ion. The measure equivalence class of I1/4 is uniquely determined and the measurable family HXX is determined almost everywhere with respect to I1/4. Example, structure of the Laplacian equals, the Laplacian on Rn is the operator. As remarked above, the Laplacian is diagonalized by the Fourier transform. Actually it is more natural to consider the negative of the Laplacian AI since as an operator it is non-negative. Theorem. If n equals 1, then AI has uniform multiplicity mult equals 2, otherwise AI has uniform multiplicity mult equals I per mil. Moreover, the measure I1/4 mult is Borel measure on 0, A. Pure point spectrum. A self-adjoint operator A on H is pure point spectrum if and only if H is an orthonormal basis AIOI consisting of eigenvectors for A. Example. The Hamiltonian for the harmonic oscillator has a quadratic potential V, that is. This Hamiltonian has pure point spectrum. This is typical for bound state Hamiltonians in quantum mechanics. As was pointed out in a previous example, a sufficient condition that an unbounded symmetric operator has eigenvectors which form a Hilbert space basis is that it has a compact inverse. See also, compact operator on Hilbert space, theoretical and experimental justification for the Schrödinger-Dingo equation, unbounded operator. References: Akiza, Ann I. Glasman, I.M. Theory of Linear Operators in Hilbert Space. 2 volumes. Pittman. Berezin, F.A. Schuben, M.A. The Schrödinger-Dingo equation. Kluwer. Kato, T. Perturbation Theory for Linear Operators. New York, Springer. Hall, B.C. Quantum Theory for Mathematicians. New York, Springer. Reed, M. Simon, B. Methods of Mathematical Physics. Vol. 2. Academic Press. Teschl, G. Mathematical Methods in Quantum Mechanics. With applications to Schrödinger-Dingo operators. Providence, American Mathematical Society. Yoster, K. Functional Analysis. Academic Press.